Okay, I think we can start already. So thank you very much for being here on a Friday. Today we have a speaker, Iván E López. He has been visiting us during this week. He studied his PhD in Bologna, and now he's continuing there as a Cassini Fellow.
Cassini Fellow.
Okay. So today he's going to talk us about the AGN feedback in low-luminosity AGN. So, whenever you want.
So, yes, I wanted to start with the classical view of AGN. Probably you already saw this a lot of times, right? But what is important here is just the AGN is like the combination of a lot of different structures near the supermassive black hole, like the broadline region, the accretion disk, the dust totals, and all of these produce different emission that you can appreciate it in a spectral energy distribution, right? So the accretion disk produce some of the black body radiation that peaks in the UV optical that you can see here, right? The hot corona produce non-thermal X-ray emission. The torus absorbs these UV optical photons and they reprocess it in the infrared. And after you can have also a relativistic jet that produce non-thermal emission that usually you detect it in radio, but theoretically they can cover from gamma to radio. So SED fitting usually is used to provide a lot of information of AGN properties like inclination, obscuration, and the luminosity. Why is important to study this AGN? Well, because right now we are talking that the AGNs are not just curious galaxies, weird galaxies. Their evolution is linked to the host galaxy evolution, right? In this co-evolution framework. But there is a lot of evidence, like for example, scaling relations between the masses of black holes and their hosts. Also scaling relations between the star formation rate and the black hole accretion rate during cosmic times, the need to quench these high mass galaxies in simulations, and of course, a lot of direct evidence of the AGNs doing some stuff that suppresses star formation or enhance it. So that's called AGN feedback, right? So basically, AGN are active players in galaxy evolution. That's the point here. But what I want to focus in this talk is that AGNs are not always so active, right? So the two pictures of the black hole that we have are from black holes that are not quasars, are not Cipher galaxies, are just low-accreting black holes, right? And what we see a lot with the quasars and Cipher galaxies, these high accretion scenarios, that lasts only between 5 and 10% of the duty cycle of an AGN. So most of the time, the AGN is just, the black holes are just in a low accreting phase. So the question here is, can these long phases influence the coevolution scenario? And to reply this, we are doing this different approach, two different approaches. First, understand the low accreting black hole census. And second, understand the feedback process that this black hole population can have. So why we care about low luminosity AGNs? Well, I told you before, right? So most of the time, a black hole is just a low accreting black hole. And that's translating a luminosity function, right? And eventually the Eddington ratio distribution. So basically what we consider quasar and Ciphers is just this small part of the full distribution of black holes, right? And this is valid for all redshifts, right? You can see that all these accretion below 10 to the minus 3 are dominant in a luminosity function. And although this is a larger population, it's very hard to study. Basically because it's faint emission eventually, because X-ray surveys, that is one of the less biased way of studying AGNs, and at least until the little red dots, but I will not discuss this. But usually set a luminosity threshold. to separate the X-ray emission from AGN from other contaminating that comes from the host galaxy, for example, X-ray binaries. So usually they put a threshold, for example, 10 to the 42. So everything that is below usually is the definition of low-luminosity AGN. Radio surveys also face redshift and deepness limitation, right? And also they can have like a star formation as a contaminant for the detection of these low-luminosity AGNs. And another thing is that the unified model have a lot of problems to explain this, right? I will go this after when I discuss the feedback modes, but basically the unified version that I showed you before is not so like that for low luminosity AGNs. So my point here is that without the low luminosity AGNs, any AGN census is not complete, right? And here you can see in pink the Sloan quasars, and in yellow the BUS survey, and Luso is like a sample of quasars, and López 23 is what we did 2 years ago with mini JPAS, that we tried to go to values lower than -3. But eventually what discovered right now is very the high accreting ones, right? And for reference, this is M87. So we have the picture of a low accreting black hole, but we don't know the full scenario of the census, right? So what I want to tell you is that this is why we have a lot of difficulties. SED fitting could be a very good tool to get information about this population. Why? Because in an SED fitting, you try to fit the host galaxy at the same time the black hole, and that could help you to separate the emission that they both have. That could be from the same order of magnitude for this type of sources, or even the AGN could be lower, right? So usually what the people do is try to grab like a less biased band, like for example X-ray, and they say, with an X-ray prior, I can try to guess how will be the SED of the optical bands that is competing with a host galaxy, right? And try to constrain some values for that. The problem is that SED fitting codes usually are done for standard AGNs, like high accreting ones. So they assume a standard accretion disk, and they assume relations that they are very well studied for quasars, but they are not studying the low luminosity regime. So the X-ray prior, how it works? Well, this is how it's coded in Cigale. That is where we did the main modifications. But basically, they depend on this alpha-OAS, that is the slope between the luminosity in the UV and the luminosity in the X-rays, right? And this has like a physical reason, that because the X-ray corona, the photons, are reprocessed from the seed that is the accretion disk from the UV, right? So it's the same, one is the reprocessor of the other photons, right? That's why there is like a relation there. However, if we go for the alpha-OAS and we compute it with the Ellington rates, you can see that below 10 to the -2, that is where low luminosity start, there are no points, right? We don't know what is going there. So what we expect from an SED, from a low luminosity AGN, you can see it here in pink compared with other sources, right? So first of all, we have the lack of this big blue bump that is associated with accretion disk, these UV photons that they come from the inner orbits of the accretion disk. Instead, sometimes you have a red bump that is between 1 and 10 microns, right? You can see it there. It has harder X-ray spectra and brighter radio emission, right? So what's the situation here is that the standard accretion disk is not the only way that the black hole can accrete, right? And that explains why there is the lack of big blue bump in these sources. Basically, when less material is falling, the accretion becomes advector dominated, and this is like this ADAF type of accretion. So the ADAF, as I telling you, right, are prevalent in low accretion values. They have lower radiative efficiency, but could be higher than previous assumed. So you can see here the efficiency and the accretion. This is the accretion, the typical accretion disk, and these are different models for ADAF. So you can see that the values of the efficiency are not very well constrained. But basically, they come from like a hotter, non-thermalized gas that they produce a lot of non-thermal radiation. And you can see the expected ACD for the classical accretion disk and the ACDs from different areas here. And to complicate even further, an accretion disk and an ADAF can live in the same source, right? So you can have like an accretion disk that is truncated and one radius, and after an ADAF starts. So this is a scenario that you have half accretion disk, but you don't have the inner orbits. You have just the ADAF there. So what we decide to do is to put these seed photons in the CD fitting codes, right? So Cigale works with two different accretion seed photons that is come from Skilton and Sherman from the 2005. And what we decide is to modify them to be consistent with possible ADAF. But the problem is that you can have the ADAF, the truncated disk, and you can have just the accretion disk. So it's a little bit hard to put everything in the same framework. So what we did at the beginning was like just grab this mean ADAF that is fitted for like 10 galaxies from like a physical motivated code in NMN 2014. And we say, okay, this is our pure ADAF, right? We just parameterize this. And we implement this value that goes from 0 to 1, that is delta AGN, that if it's 0, we have the pure ADAF. If it's 1, we have what Cigale was using before, the pure accretion disk. And in the middle, it tried to mimic this change of photons from one to the other, passing from different stages of the truncated accretion disk, right? With, you can see, between a bump between 1 and 10 microns, that is this larger orbits of the truncated accretion disk. Of course, this is like a parameterization. This is just the connection between a mean ADAF and what is using in the literature today to fit classic AGNs. There is a lot of physics that they are buried here, right? Because we know that these 4 power laws, that is for the accretion disk, in theory change with black hole mass, right? The position. But because you are trying to get the integral values of this, you don't pay attention too much to this. So basically, what you are seeing in any Cigale run of AGN of coevolution studies is assuming these 4 power laws, right? So they are not assuming a real accretion disk with possible changes of black hole masses. So the idea is try to do a similar approach to low luminosity AGNs, like simplistic approach, just to try to get the average integral that these sources have. We are focusing not in the physical quantities, but we are focusing like black hole mass or even the accretion disk. We are trying to get the luminosity, because that's what we will compare with the typical studies of coevolution. Another thing that we did is not use the X-ray prior with the UV, because we know that the UV is problematic in these sources. So what we implemented here is the X-ray to 12 micron relation, right? This is like it's going for a while. This relation is almost linear, and it's a very good fit. And the physical explanation behind this relation is that the X-ray are reprocessors of the UV, and the infrared are also reprocessors of the UV. So we are not assuming any UV distribution here. We are not going from X-ray to UV that we don't know, but we expect that if there are some UV, they are being reprocessed in the same way for X-ray and for mid-infrared. Juan Antonio here, he published a paper a few years ago where like he showed that for his small sample of low luminosity AGNs, they follow this relation. So we base on that this relation is valid for them. And also is valid until mid-luminosity, so 10 to the 45, 10 to the 46, but this covering also mid-luminosity AGNs. That is very good because we have also a sample to calibrate these things. So you cannot see very well here, but these are like examples of the SED that we are doing now, right? In red, these were like the delta values of 1, so the previous Cigale model, where you can see that you have, here there is a line, I will show it to you, but imagine that is there. This is, you know, like a typical AGN without outflows, with a strong UV field, and that reproduce the type 1 AGNs, right? And here you can reproduce a little bit the type 2, that they have obscuration and they have a lot of infrared emission. So when we go to our model, now we are just pay attention to values between 0 and 0.8. You can see that you don't have any huge UV here, right? You are more in the type 2 scenario, but with an intrinsic less efficient UV photons, right? So you don't have after a lot of dust heated. So it's like a little bit better for work with these sources, because if you are just fitting this type of SEDs to these sources, you will have like a offset in the infrared or offset in the UV, right? And after we can also recover a little bit the possible red bump between 1 and 10 microns here, you can see. But to do this properly, we need to do a more validation mock, right? So we simulate a lot of galaxies, 360,000 of them, and we try to recover the values that were the input after the SED fitting, right? And you can see that after you do the SED fitting for these galaxies, that you know which values you put, most of the model falls in the 1-to-1 line. We know that we are slightly biased to higher values of delta, and this alpha IRX is just how much scatter is from the X-ray to 12 micron relation. But what we are interested is in trying to recover the luminosities of these sources, right? So here you can see the luminosity, the best fit minus the true one in this mock catalog, and here is the fraction of AGN. So the AGN, how much dominate the AGN con respect to the host galaxy. And when we are in like, this is separated for star-forming galaxies for quiescent, right? Because star-forming, they will have more blue color, so will be a little bit harder to fit. But basically, in high values of fraction of AGN, you can see that we can constrain very well the luminosities. And even when we go to lower values, you start to have like more degenerated model, but the mean and the quartiles of this difference are within 0.5x for all the things. So overall, it's you know, it's the first step. It's not so good, but it's some. It's better than just fit a template of a real AGN, like a high accreting AGN. The only problem is that if you go to very low values, you start to have tails of models that they are not true, right? And they are like more than 1x difference. So after that, after all the thing, we focus on trying to do some science, and we choose like a sample of 50 local galaxies that they were cataloged by low luminosity AGNs in the community. So we are extracting photometry in 9 arcseconds radius because we want to grab from the UV to far infrared, right? You can do it better if you exclude the far infrared, that the PSF is terrible. We performed the SED fitting and we got what we were expecting, right? So volumetric luminosities that they go from 38 to 43, and Eddington ratios that they go below -3. before talking about the results, I want just to say that we did some validations with these mid-luminosity AGNs with ciphers where we can match the luminosity from the literature with our luminosity. And this is for the sample of low luminosity AGNs. And you can see for all the low luminosity AGNs, the reference value in the literature was higher than ours, right? That doesn't mean that it's true, right? Because most of these values come from scaling relations that again they're applying for high accretion sources. But so we were happy with the validations in the cipher plane, and after it's like, okay, let's discuss these changes of luminosity for our Taylor model for these sources. So this is two of the main results of the paper, like talking about science. This is a sample of 50 low luminosity AGNs. Just to give you a context, other works they are working that they are like tailoring much more than us. They are working with 8, 10, 12 low luminosity AGNs. So this was like a larger population, but this opened the possibility that SED fitting you can do it for 1,000 sources without any problem, right? So it's just the first step in that direction. And from that, we got that the X-ray volumetric correction, for example, you can see this is the quasar regime, right? The very high luminosities. And there was this extrapolation of Duras 2020 that they say, okay, here the X-ray volumetric correction, right, looks constant. And we are kind of an agreement with them, right? Looks like more constant, the X-ray production. The huge difference is in the alpha-OX, right? So the alpha-OX here, this is again the quasar regime, and usually what they say is that there is this slope between the alpha OX. This is the data from LUSO 2010, that is quasars. And what they claim in their paper is like, okay, alpha OX changes here because the UV photons became dominant against the X-ray photons, right? The big blue bump is much more dominant, and that's why the accretion changed the alpha OX. What we are seeing in the low regime and with huge error bars, but we are trying to get some statistical value here, is that for us the slope is not so clear, and it looks like it's like this broken power law that here has a slope and here is just getting flat, right? This could be like this shift of photon production that is like what everyone else is assuming for these sources. So the conclusions here of this paper is try to focus on a tool to understand the census of low luminosity AGN, right? So, and having non-standard accretion and not relying in quasar extrapolation, right? So this is, we believe, the best tool to do and work with Cigale, that is like, one of the most famous SED fitting code today, to grab it and say, okay, I will just run with different values of delta, not assuming that my population is a quasar or is a low luminosity AGN. So we recover for the mock galaxies, we have like good estimation at least of the luminosity of the AGN. And after we start to study a real population of low luminosity AGNs, we get similar volumetric X-ray corrections to what they were publishing before, like from like extrapolations, but changes in the alpha OX versus editor ratio versus the accretion, right? Today with this project, the idea is to expand this to radio, that is the other big unbiased band for AGN, and try to incorporate the jet emission and radio relations. And of course, keep working with fitting a large quantity of low luminosity of AGN, including this model. So we can start to talk about not 50, but 100 or 1,000 of these sources. For this, you need, large surveys, but with Rosita and X-ray and JPass, Euclid, you can start to do this type of things now. The second part is discuss what is the feedback of these sources, right? Because if we want to know if these black holes influence the coevolution scenario, we need to understand how many and what is the feedback, how they are like modifying the parameters in the host galaxies, right? So this is just a very simplistic view in how the AGN affects their host galaxies. You can separate the feedback in two different modes. A radiative mode that is associated with high accretion rates, so again, quasar, where the radiative pressure expels the gas, right? They produce these outflows that they are driven by the radiation of the accretion disk, and that were the dust and the gas that you were using for doing a star formation after, right? So you miss the reservoir of to do the star formation. The kinetic instead is associated with the high energetic jets, and the jets produce cavities, shocks, and turbulence, right? And eventually they hit the gas, and the gas needs to cool down first to form the stars. So while these two pictures point to a negative feedback, so like suppressing the star formation, we have a lot of examples of positive feedback, right? Where like the turbulence, the compression of the ISM generate an episode of star formation. And there is also even in the same galaxy, both modes can coexist, right? So you have a positive feedback in one direction and negative feedback in another direction. So the reality is much more complex than this one. And also, it's not one or the other. There are galaxies where these two modes can coexist. In low luminosity AGN, this picture changed a little bit because the structure of low luminosity AGN is different than the unified model that I was telling you before. For example, the broadline region disappears because you don't have this radiative pressure to keep the pressure on this material, right? And the dusty torus is uncertain. There are papers that they claim that it's not there. There are also some observations that they detect nuclear dust. So this is a type of situation where the people didn't agree yet. Let's see that maybe JWST changed that. And also that the ADAS favor jets. So we are a little bit more inclined in the kinetic feedback. So, you know, you have these M87 beautiful jets that they impact the AGN, right? This is in like very powerful jet, radio loud galaxies. But the radio quiet galaxies with an AGN could have like, you know, low power, non-relativistic jets that could be contained inside the host galaxy. And that can displace dust, can compress, can inflate the radio bubbles, and that can impact the ISM in a similar way, right? And there are also some theoretical works that they are saying that the winds from this INAF can also suppress the star formation. So we have like the tools to say that there is feedback in these sources. So JWST show also high ionization outflows in low luminosity AGNs, in particular in Sombrero Galaxy. That is the evidence that low luminosity AGNs can drip ionized gas, even if you don't have the radiative pressure. So the idea here is that because these galaxies, they are not showing these ionization cones like you can see in JWST with for Cipher galaxies, is that the energy released in low luminosity AGNs is mainly kinetic, right? So our target is MF58. It's a massive galaxy in Virgo. It's LLAGN, or you can say also Cipher 2, but it's low luminosity with an X-ray of 10 to the 41 per second, and has like evidence of like another. Has also a low power radio jet with a lot of H2 emission lines. This means that there are like shocks there, and disturbed CO. So there is a little bit of a mess in the center. So this is like the perfect laboratory to study the feedback, because we have a low UV field radiation, but also a low power jet. So last year we published this paper with like the view from a Spitzer. And from a Spitzer we have like the data cubes. They capture the central kiloparsecs and even a little bit of the spiral arms, right? And from there you can extract the spectra of the spiral arms and plot it, right? And you can see these path features here, and this small here is the emission line from H2. And after you can see the center, and you can see that this small feature of the H2 is huge, right? It's completely dominating the spectra. So it's basically between 3 and 25 times higher than the typical ratio that you expect from a star formation region. People, PDRs, right? So if you fit some models here, you will see that the temperature there in the spiral arm is just 50 kelvins, while in the center there is like between 150 and 300 kelvins. So there is a lot of evidence that something is going on there. So what eventually we conclude is that the picture was revealing this extended emission of shock gas. And we went to see with a higher resolution with Gemini, and we asked the images of the H210S1 in 2 microns. And you can see that the image matched completely here in blue with the dust lanes from the CO, right? But these dust lanes are very cold, but this is warm. So this was in agreement with the low velocity shocks. And the idea is that we match the morphology to some simulations, and the idea is that you have this shed that is going perpendicular to the plane of the galaxy, and you have the dust lanes that they are being shocked by this inflate bubble that the radio jet is doing, right? The important part here is that here in the ISM, the warm molecular hydrogen is the main coolant of these regions, right? So if you are not looking for hydrogen, you will miss, because in CO it doesn't look shocked, right? And now we got some beautiful JWST images with much more resolution and with almost all the instruments. Here you can see in red the PAHs, right? They are like the spiral arm of the galaxy, that they are like converging in this type of inner disk that we were resolving before. You have in blue the old bulge of the galaxy, you know, the old stars from the near infrared, and in green you have the images of the H2 emission. So, you know, before we have this Spitzer data cube that we try to get all the data. Here is in red is neon. In blue is the PAH, and in green is the H2. This is the jet orientation, by the way. This was the imaging of Gemini, and this is now with the JWST. This is with MIDI, but also from this part of the center, that is like almost 700 parsec, we have data cubes from NearSpec and MIDI, right? And with that, we are doing a lot of things. These are the spectra of the nuclei in orange, and a ring of ISM around the AGN, right? And you can see that you have in the, let's start with the spectra, with the nuclei, you have a Paschen alpha here, you have a CO absorption bands here, you have a continuum that is growing, and eventually you have, like, you know, the lines of INS gas here, 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 here. They are very, like, they are, I would say, the dominant emission in this spectra, with a silical bump in 10-9 microns that is showing a lot of hot dust there, right? There is also H2 emission in all the places, but the H2 emission is much larger in the ISM. So the ISM, you have, like, you know, the last part of the stellar spectra, right? Stellar continuum. You have also some CO absorption. And after you have like pro-vibrational lines of the H2 and all the ladder of rotation, new rotational lines. They are like completely dominant with respect to the nuclei, right? We have also some PAHs, so there is a lot of things going on in this spectrum. And these are like some momentum maps from the H2. These are just some of the rotational lines, just from MIDI, right? And there is a small dot that is, you know, the radio emission from the AGN, the center of the AGN. And here you can see in the fluxes how the lower transitional levels, that they are more cold, are dominating in the dust lanes. These are like the same dust lanes that we were seeing before, but it's just the part that is conversion to the nucleus, right? And eventually you go to higher in energy, and the nucleus start to pump up a lot, and the dust lanes, they became a little bit more compact, right? Even if you arrive to SA, that is very high ionization power for this excitation, it's very hot gas, and you have detections in mid even. The velocity fields, they show like a very nice story, right? You have like velocities between 300 kilometers per second. So you don't have this, for example, this outflow that they were seeing in Sombrero, that is like 1,000 kilometers per second, or like also for the more like quasars of scissors, that they have like, you know, very high velocity outflows. Here is just as quiet rotating galaxy, right? With the velocities that they make sense for like this type of galaxy for the rotation. So these are the dust lanes. They are like rotating across the galaxy, and you also go higher in ionization, and you eventually in SH see a small ball here next to the AGN with like with velocities that are completely offset with the rotation, right? This is our main candidate for an outflow, we want to say, but it's an outflow of 300 kilometers per second, so it's not huge outflow. The dispersions show the same story, right? The dust lanes, they have lower values of dispersion. So it looks like the kinematic that the galaxy had, they are not affected by the shed. They are like having a slightly higher values of dispersion close to the nuclei, but this is like a very small scale. It's like, you know, we are talking about the central 400 parsecs of this galaxy. This is a plot that is one rotational line against the other of the H2, and usually it's a tracer of temperature. And when you see that, you see that the temperature in these two bumps next to the AGN is kind of here. So this is almost inside the AGN or close it. This is a little bit farther away. This is like 150 parsec. They have like a very strong temperature, like high temperature. And the dust lanes, they are a little bit also, but not so strong like this part. And this is a diagram that I put just in case you don't know the lines of the H2, right? This is what we are seeing with MIDI. It's like the first vibrational level of the molecule and these rotational values, right? The interesting part, this is usually the main excitation mechanism is collisions, are shocks, right? But with NIRSPEC, we can resolve all of this. So we are starting to see much more in the different excitation mechanism that this galaxy is happening in this galaxy. So we start to extract different regions, and we start to plot these excitation diagrams, right? This is like the ladder for for rotational lines, pure rotational lines, the ones that you see in blue. So S1 to S13 and S13. You can model that with a single model of temperature that it comes from the model of Toby Smith, and with that you get density and temperature. You can see that usually we are modeling well until S13, but now we did some modifications to their code to add a little bit more higher temperatures, and we are fitting this without any problem. The situation is very interesting with the raw vibrational lines that they are here, right? So we plot the density values for them, and you can see that the lanes, right? Here is the northwest lane that is here, and this is the southern cloud. They also follow like a trend of like a power law here. But look the nuclear, right? The nuclear doesn't follow the trend. The nuclear has a lot of high vibrational levels that they don't agree with this thermal behavior. And first, what we did, we just modeled the rotational lines just to get instead of talking about ratios, talking about physical quantity. So this N is tracing the mass eventually, right? The density, and these are the temperature. So now we are modeling with the temperature what we were seeing before with the ratios, right? So we know that here are like very high temperatures, and the dust lanes are like a little bit lower, but this is consistent with what we were seeing with the Spitzer, right? This is a shock molecular gas that is heat up. The density shows also a nice story because the dust lanes have like higher density. You were expecting that, but the nuclei has very low values of this power law index. Also, the two clouds here. And after we went back to ratios, because this, but if you use the ratios of NIRSPEC, you can get a lot much information of what are the physical condition of the ISM around the AGN, that is marked in white here. So this is the second vibrational level against the first one. Basically, what you expect is that higher vibrational levels are hard to explain with collisions, but they are much easier to explain with non-thermal process. So a value above 0.5, 0.6 tells you that you have non-thermal excitation. This code could be cosmic rays, UV pumping, or XDRs. This is a density proxy, right? So you can see that after the shock is done, you can see the shock here in the map of temperature, there is an increase of density just in the border, right? You expect that if you have some compression after the shock. And this is, again, the same radio that I showed you before, but I am doing a zoom in for this small thing. And this is like the orthoparal ratio. Basically, it's the relation between the even numbers of the rotation and the odd numbers of the rotation, the lines. And theoretically, this is a value that is 3. You don't have 3, you have less than 2. But these two blobs greens, they show you values lower than 2. When you have non-thermal equilibrium, or you have non-standard H2 creation, right? This could be both scenarios, because here you have the shock. The shock maybe is destroying the H2, and the H2 is forming after. So this is a very nice result, because if you see the drop in the equilibrium is done before, like in the post-shock, you have the shock, and after the pre-shock. And this is one of the final things. Is just an RGB imaging using the lower rotational level detected by JWST, the lower vibrational level detected by HST, tracing a little bit higher temperatures, and the shocks here. Patient alpha in blue, you can see it here, and the UV contours from HST. And what is saying that the UV contours are just between the shocks, right? Like if the star formation is there between the shocks, right? So we can have, if we are assuming that we have some compression in the shocks, that could pump up some star formation, so we can have like some positive feedback. And another thing that was very interesting that we were discussing with Juan this week is that just after here in the shock, where this is a small opening, there is this bihorn emission lines in all the emissions, all the molecular hydrogen, but also in the inner space. So you can see very high vibrational lines, right? 10, S3, S2, S1, and then also higher values of the excitation of the H2, the pure rotational lines, S11, S10, S9. But this repeats across all the spectra, all the H2 lines. Like if there is something disrupting the kinematics there. So the scenario that we are proposing now is that you have, in the Spitzer view, you have this cocoon of 2.6 kiloparsecs that was inflated by the radio shed, and you have the dust lanes, and the dust lanes were just hit up by the shocks. Now we are resolving this much better, right? So we can see the dust lanes that they are like maintaining their dynamics, maintaining their values just with higher temperatures. But there is a front shock that is impacting the ISM and changing the dynamics in the 100, 200 parsec. And inside that bubble, there is like this non-thermal emission that is hitting the H2 with, we assume, XDR because it's a little bit more probable. So here I'm doing some numbers now, and I find out that with XDR you don't need to assume anything crazy, but with UV pumping you need to assume crazy couple efficiencies. So I am more inclined for XDR, but it's not final. So this is like what we are resolving today with JWST. I gave you like my TED talk about M58, right? And the question that you will tell me is M58 an extreme case or is just a normal low luminosity AGN? So these are the ratios of H2 emission against pH, just to normalize by quantity of dust, and that separates shocks and non-shocks. And this is the pH 7.7 with the pH 11.13, that is separating kind of star-forming galaxies with no star-forming galaxies. You can see M58 is there in one of the corners, very shock, very star-forming galaxy. But around the M58 are just the 3C catalogs, right? Radio galaxies with with order of magnitude higher than M58, radio low galaxies. So I'm showing you that I have a similar feedback effect with a much weaker radio shed. And there are a lot of other galaxies that they are aligned there, right? There are a lot of low luminosity AGN sensors that they could have a similar feedback. But this feedback is just visible in infrared for now. So the conclusion of this is like this was like the first paper that we published with a Spitzer view. The radio shed is inflating this cocoon, and this is impacting the dust lanes that they were already there. Overall, the star formation seems suppressed because we do like some pH ratios in all the area, and looks suppress the star formation, so negative feedback. A lot of turbulent motion from ALMA is also detected there, so the cold gas eventually is getting turbulent because of this feedback. And now with the JWST, we can resolve this feedback up to 10-20% of the galaxy, right? Where the dust lanes, we are confirming that they are retaining their properties, just being heat up. But even the dust lanes, that is like, you know, where you expect to have this cold molecular gas, they have like high rotational H2 transition. We need to remodel from the previous models that they were there. So we are talking about 3,000, 4,000 kelvins. High levels of vibrational levels for H2 emission comes from the nucleus, right? Suggesting non-thermal emission there. The nucleus also show lower gas density, but after that, the outskirt of the shock front shows like enhanced density. So that we are thinking that we can show some evidence for compression there. The UV there, the UV emission traces the same star formation ring that is just outskirt, is between the shocks, right? So we can have like this scenario where like shocks are coming, and you have like positive feedbacks in between events of shocks. The question remains, how common is this feedback in these low luminosity AGNs? And that's, I think, what we need to start to think now is how much of these galaxies they show this feedback, because that will give us the answer if this feedback is relevant for galaxy evolution. Thank you.
Very much, Ivan, for a very nice talk. Questions? I will start with one.
Sure.
Have you done, or can you do some energy balance, trying to compare the energy that you find in the ISM, that the energy that it's affecting the H2 compared to the jet power?
Yes, we did it for the Spitzer data, and you just need 1%, 0.1%, I think so, of the jet power to explain the H2. That's why at the beginning we suggest that the jet was doing everything, right? Because it's hilarious how much energy it's putting. It's minimal and it's giving like so much excitation.
And
Sorry, we need to do it now with better resolve the data, right? because that was like larger scale, but now we can do it for almost every cloud.
Have you compared the coupling factor, so the fraction of the jet energy that finish in the ASM, with the coupling factor in more powerful radio galaxies?
Not yet.
But that would be an interesting thing to do, to check if these guys are more efficient than the high power jets.
Yes, that is clear. Yes. Well, we can do it because the paper of Patrick in 2010, he's working with the 3C catalog. So we have the data from there.
And the other question is about this region with the two peaks in the H2. How did the rotational the Boltzmann diagram look for those peaks? Do you have it?
I don't have it yet.
But it would be interesting to compare with the rest to see if.
Like I did it for the northeast shock, I need to do it a little bit above, right? But yes, of course.
Yeah, just to know if it looks like shock or it has something else.
Yes, I agree.
Come on, guys, don't be shy.
Okay, yeah, well, out of curiosity, because this is far from my field, you're playing with very dusty galaxies, right? And when you are using the spectral energy distribution in different regions, are you able to model correctly their differential reddening? Or is a bit of a nightmare to do it right?
So for the SED fitting, we are just grabbing the aperture, right? So I am not doing any differential studies.
Okay, but
it's just
when you are looking at different parts of the galaxy, I believe that the reddening changes, the intrinsic reddening that you have in the galaxy.
Yes, probably. But like for the SED fitting, right? I am just focusing in the center. I'm not doing any resolve SED fitting.
Okay, so you just correct the reddening we have from the Milky Way, not in the galaxy itself.
The SED fitting has the module for the intrinsic extinction, right? But yeah, I correct for the Milky Way, and after I leave the SED fitting with some free parameters to do itself.
So the part of the reddening, so how Cigale works is doing energy balance. So you fit what you see in the ultraviolet, the code finds the extinction that it needs, and this is tied to the emission in the far infrared. So if you have too much dust to correct the ultraviolet, you will have a model that it will have a lot of far infrared. So if you have both infrared and optical, you can constrain a little bit better.
That's why I'm working. I am like, accepting bad PSF from far infrared just to leave Cigale to work properly. If I cut that, I don't have the bump of the infrared emission.
Okay, and I believe getting high resolution spectra for these galaxies is expensive. Like you need, again, the photometry is cheaper, right?
Yes.
So
we did some proposal to JWST just for a couple of galaxies.
That's what I mean.
Yes, and yes, it's expensive. Was like, I don't know, 90 hours for like 6 galaxies.
Cool, thanks.
And sorry, just the central kiloparsec, right?
Yeah.
Questions?
So thank you very much for the talk, very interesting. So from here, I mean, the complexity of the central part is huge. You have a lot of information, but at the end, you go to higher resif or let's say set fitting. I don't know if at the end you can find something, some property that can tell you about the positive feedback, negative feedback. I don't know, the UV ratio with respect to whatever. I don't know if.
Yes, that's the idea. Is to try to study this close by in detail, just to try to get a tracer of this feedback. Right? If I can understand, for example, here you can see there is two lines that are very high above the rotational, right? So if I can start to say, these lines are the ones that we need to look for. I don't know if we will resolve this line in a higher redshift galaxy, but it's there, is that thing. So after with models, you can say, if I can constrain this line, maybe I can find another thing. So for now, we are just focusing in the local universe. There are people that are doing low luminosity agents in cosmic noon, not high ratio, but cosmic noon.
But even if you cannot resolve it, this is very useful to feed simulations. Because prescriptions are largely unknown. So if you can have a prescription for the feedback from these low power jets, that will be very useful for when they implement the feedback from those kind of objects in a magneto-dynamical simulation.
Yeah, of course, cosmological also.
Okay. I have another question from the first part of the talk.
Yes.
Go to the figure with the alpha X. This one is very interesting because you find that below 10 to the minus 3, where the accretion disk is supposed to disappear, there is no longer a dependency between the alpha X and the Eddington range. I remember a plot like this from Dan Mao, and he had much less objects here, but he was arguing that the similar alpha X between relatively similar alpha X between liners and Seifert was an indication that there is still a little accretion disk in these guys.
Yeah.
But I think this proves otherwise, no?
Yes. So here I plot also the plot of Shu, right? That he is doing the opposite. He's saying after you change the accretion mode, the alpha X start to grow again. But at least the paper from Shu, they have also 20 low luminosity gens, but their UV comes from H beta. They are doing a proxy of H beta to UV. So exactly, it's okay, you are just
using a recipe.
Yes. So the one of mouse, yes, also because the first time that I did the fit, my alpha X were here. Right? And I was like, okay, I remember now. This is perfect. After a person suggests, why you don't model the alpha? Because I was not modeling the alpha before. I was just adding a small accretion, the typical recipe. And after we modeled the alpha, we went down. So yeah, if this is constant, right? It's okay, the UV photons are independent. So the process of the ADAF is not changing with accretion. And if you remember what I showed you in the beginning, these were some other models. These were different models for the ADAF, right? And you can see that they are almost pretty plain SEDs, right? So and these are different values of accretion, one order of magnitude, all different. So makes sense for a theoretical point of view.
Yeah, when the disk appears, this slope becomes steeper.
Exactly.
Okay. Anything else? No? Thank you very much. You are dismissed.